Hello, my name is Vardoyan, and today I will present our work titled On the Capacity Region of Bipartite and Tripartite Entanglement Switching, done in collaboration with Saikat Guha, Philippe, and Towsley. In this talk, we will focus on a single quantum switch that serves bipartite and tripartite entangled states to users that are connected to the switch via dedicated identical links in a star topology as shown in these graphics. Due to the time constraints, I will not cover background details here, but refer you to the first few minutes of our other talk on the exact analysis of a quantum switch for a brief background on quantum computation, communication, and entanglement switching. The rest of the talk is organized as follows. First, I'll introduce the problem. Then I'll describe the operation of the quantum switch and introduce our model, analysis, and results. Finally, I'll conclude with a summary and future direction. In much of our prior work, we focused on bipartite entanglement distribution between two users. This process works as follows. A quantum repeater or switch is positioned between the users. Bell pairs are first attempted at the link level between the users and the switch. The switch then performs local operations and a measurement, collectively known as a swapping operation, the result of which is a longer distance bell pair directly entangling the user's qubits. This new bell pair can now be used as an expandable resource, for example, to teleport qubits or to help generate secret key bits. This process can be generalized to entangle more than two users. For instance, a GHZ projective measurement can be performed to entangle 3 or more users and generate an n-partite GHZ state, where n is the number of qubits. These states have many uses, which include multi-party quantum key distribution, quantum secret sharing, quantum sensing, and multi-partite generalization of superdense coding. End-to-end bell pair and tripartite GHZ state generation are the focus of this work. Specifically, we will examine a quantum switch that can serve either bipartite or tripartite entangled states to users that are connected to it via dedicated links. In this example, there are 5 users, and sometimes the switch performs a bell state measurement to entangle 2 users' qubits, while other times it performs a 3-way GHZ projective measurement to entangle 3 users' qubits. The first goal of our work is to characterize the capacity region of a switch that operates in this manner. In other words, let's look at a plot with bipartite capacity on the y-axis, which we call C2, and tripartite capacity on the x-axis, which we call C3. These are the number of bell state measurements and GHZ projective measurements that were served by the switch per time unit, respectively. We are interested in the profile of the capacity region, generated by various entanglement switching policies. The first observation is as follows. There exist maximum values for the bipartite and tripartite capacities, which are achieved when the switch serves only bipartite or only tripartite entangled states to the users respectively. We label these maximum capacity values C2 star and C3 star. The next observation is that there is a set of switching policies that result in capacities which fall on the line connecting C2 star and C3 star. These capacities can be obtained simply by having the switch multiplex between bipartite and tripartite entanglement switching. So we call this line the time division multiplexing or TDM line. It's easy to see that the capacity region below the time division multiplexing line is also achievable. It's also easy to see that the gray shaded region represents an inaccessible rate region, because we can't exceed the maximum bipartite or tripartite capacities. What's harder to see is whether we can achieve any point in the pink shaded region. In other words, do there exist any entanglement switching policies that perform better than the simplistic time division multiplexing set of policies? Before we can answer this question, we have to make some assumptions about the architecture and operation of our quantum switch, which we will now do. Since we're interested in the performance of the switch, we assume that the user's capabilities are not limited. In other words, the users have an infinite number of quantum memories with infinite coherence times. We assume that the switch is equipped with some number of quantum memories as well, which we sometimes refer to as buffer. Each link is allocated b+1 quantum memories, b of which have long coherence times, and 1 that is short coherence. In this graphic, the switch has 1 long and 1 short coherence memory per link. Sometimes I'll refer to this as a buffer size 1 system. Gray circles represent unoccupied long-term memories, and when they become occupied, we represent them with red circles. We also assume that the switch can perform projective measurements and is capable of classical communication. Qubits from newly generated link-level bell pairs are initially stored in short-term memories. Then they must either be used in entangling measurements or be moved to longer-term storage. If neither of these two operations are performed, a qubit that remains in short-term memory will be lost eventually. In this example, the qubit here is moved from short-term to long-term memory and is stored for later use. From now on, to simplify the graphical representation, I will only show you long-term memories, and you'll have to refer to the color of the memories to see whether a qubit is in long-term storage or not. The switch will serve k users, and its operation consists of two steps. The first step is bell pair generation over the individual links, and the second step is end-to-end quantum state generation via swapping operations. We model link-level entanglement generation as a Poisson process with parameter mu representing the rate of successful entanglement generation at the link level. We assume that all links are identical so that they all generate bell pairs at the same rate. In the second step, the switch may perform swapping operations, which happens according to user requests or a switching policy. In this example, there are two link-level bell pairs. Both of the qubits at the switch are currently in short-term memory. The switch may decide to perform a bell state measurement to entangle the two users' qubits. But another option would have been to store the qubits in long-term memory and wait for more bell pairs to be generated at the link level. In this work, we model coherence time as an exponential random variable with mean 1 over alpha. Suppose that later on, a new bell pair is generated, and the qubit at the switch associated with this bell pair is currently in short-term memory. Since the link already has a stored bell pair, and since this is a buffer size 1 system, the newly generated bell pair can't be stored. Instead, the switch may decide to discard one of the bell pairs, or it may decide to perform a bell state measurement if the two users wish to share an entanglement, and store the newly generated bell pair long-term. The result of those two operations is shown here. Suppose that instead there are 3 users that wish to share an entangled state. In this case, the switch must wait until the third link successfully generates a bell pair. As soon as it does, the switch may perform the required swapping operation to entangle the 3 users. Now we are ready to model and analyze the switch. Recall that we model link-level entanglement generation as a Poisson process, with mu the successful link-level entanglement generation rate. We model coherence time as an exponential random variable and use parameter alpha for the decoherence rate. Note that for a given switching policy, we are interested in the capacity of the switch, which should hold under any workload. For this reason, we must assume that any set of 2 or 3 users wish to share an entangled state at any given time, so that the switch is not constrained by an entanglement request policy. Also, the switch will use bell pairs as soon as there are enough to generate an n-partite entangled state, since doing otherwise would also likely result in a switching rate that falls below the capacity. Using these assumptions, we modeled the system as a continuous time Markov chain. Let's take a look at the Markov chain for buffer size 1 systems. Due to our assumptions on the system from the previous slide, it turns out that only up to 2 links will store bell pairs at any given time. So when b is equal to 1, the chain has only 3 states: 0, 0, where no link has a stored bell pair, 1, 0, where 1 link has a stored bell pair, and 1, 1, where 2 links have a stored pair each. The transitions between the states are shown here. We use parameters R1, R2, and R3 to enable a set of randomized switching policies. By varying these parameters within the interval 0 and 1, we're able to generate all possible switching policies that are representable by this Markov chain. We are now ready to answer the 2 questions we asked in the beginning of this talk. In addition to characterize the capacity region of the switch, we can also look at the effects of quantum state decoherence and buffer size on the capacity region, as well as the behavior of the system as the number of links increases. Here is the capacity region of a system with 3 links and 1 long coherence quantum memory per link. For now, assume that quantum states do not decohere. The dashed line represents the set of time division multiplexing policies, while the solid blue envelope represents the set of capacities that are obtained from various randomized switching policies, which are determined by the 3 parameters, R1, R2, and R3. We can see from this plot that these policies perform better than time division multiplexing. However, when the number of links is increased, the fraction of these better than TDM policies diminishes. For buffer size 1 systems, we characterize the capacity region analytically and show that it's bounded by the triangular region above the time division multiplexing line. We prove that there is always a randomized switching policy that performs better than TDM, and that the advantage of using this policy diminishes as the number of users grows. Qualitatively, the results are similar for buffer size 2 systems. When quantum state decoherence is non-negligible, we observe that the capacity region shrinks. This is a system with 3 links where each link is generating entanglement at a success rate of 1, for example, mega-EBIT per second. A decoherence rate of alpha corresponds to an infinite quantum memory coherence time, and so on. We also observe that the effects of decoherence diminish as the number of links increases. Further, when alpha is an order of magnitude smaller than mu, decoherence doesn't have a significant effect on capacity, and the results are qualitatively similar for buffer size 2 systems. Finally, we do a comparison of the capacity regions when each link has one long-term versus two long-term quantum memories allocated to it. From the first plot, we can clearly observe the advantages of extra buffer, but these advantages diminish when the number of links increases. Also, note that the tripartite capacity benefits more from the extra buffer space than the bipartite capacity. This brings us to the conclusion of the talk. In this work, we introduced the bipartite-tripartite entanglement switching problem and modeled a quantum switch that serves multiple users in a star topology as a continuous time Markov chain. We used our model to explore a set of randomized switching policies and found that while there's always a better policy than simple time division multiplexing, the advantages of such a policy diminish as the number of users grows. These results were shown analytically for buffer size 1 systems. For future directions, one could examine several extensions of this problem, such as link heterogeneity, non-unit quantum state fidelities, and larger buffer sizes. An interesting problem would be also to incorporate user requests and explore optimal scheduling policies conditioned on these requests. Thank you for listening, and if you have any questions or comments, please do not hesitate to contact any of the authors.